We continue our discussion with Manova, the multidimensional analog of Anova. Anova, as we all know, is the practice of partitioning the total variability in the data into different components which are due to the sources of variation. So, we have already seen that this is done with the help of a simple model as part of the estimation procedure is considered, and then for the testing purpose we need some distributional assumptions as well. So, if you recall, we had just started the discussion with the one-way Manova model. One way in the sense that there is only one factor, so we are going to split the variability into this factor, and obviously the part that comes along with it is the residual part. So, together we are going to have two sources of variation in a one-way Manova model. One is the sole factor which is present, and the other is due to the residual. So, let us just recall the model once again. We had taken that Xij, that is the jth observation pertaining to the ith group or population, is basically made up of its mean effect mu I, which is the mean effect in the ith group, and then the error present in that is the jth error in the ith group. And for the distributional assumption part, we had assumed that these errors are nothing but p-dimensional normal with mean 0 vector and variance covariance matrix sigma. Now, this mean is obvious from the fact that we have expectation of Xij is nothing but the mu I, which is the mean effect. Now, this mean effect was further broken up into the grand mean or the overall effect, and then the rest of it, the residue which remains, is the mu I minus the overall effect, and this part in fact was considered as the treatment effect or the factor effect, the only factor which is present now. So, we had denoted this by tau I. So, that the model, the one-way Manova, let us put the headings, the one-way Manova that we are consider, and this is nothing but the mean effect or the grand mean effect in fact, or the overall effect, then the treatment effect, and obviously the error part. With the error part following, we have the assumption on this part and hence an assumption on the random observation Xij's also. Now, we had also seen that if we can split our data, let us take a particular data vector Xij, and then this is analogously split it up as this is the x bar, the overall sample mean, and then we have the group mean with the difference with the sample mean, and then the rest of it which is Xij minus the group means Xi bar. So, this gives me an estimate of the overall effect, this giving me the estimate of the treatment effect Ti, and the last part is giving me the residual, and we are denoting this by Eij hat. Okay. So, our next task is to get the sum of squares due to the different sources. So, we are considering the multivariate analog of the univariate sum of squares. Let us see how we do that. So, here we will have not just sum of squares, but sum of squares as well as cross product matrices. Instead of scalar quantities which are simply sum of squares, we are going to have matrices and which will pertaining to the sum of squares as well as the sum of cross products. So, let us see, first we consider what we have been calling as the within matrix. Within essentially means this within comes from the fact that this is representing the within population or within group variability. So, that we have Xij minus Xi bar, the group means, and then the transpose over this. Sums are over. We may mention here that within a group, say for the ith group, j is going from 1 to ni, which means that it does not have to be a balanced design all the time. We need not have a constant n for all the groups. We can have for the ith population or ith group a sample size of ni, and then we have I from 1 to k, meaning that we have k populations. And for simplicity's sake, we were denoting that the total number of samples, that is when each of these ni's are summed over the k groups, we have a total of n samples. Okay. So, this can very easily be seen as a sum of terms like ni with xi bar minus the overall mean xi bar minus the overall mean transpose sum over I, and then the other part. Now, this is in fact the corrected sum of squares cross product. So, in fact, what we are considering here is the observation minus the sample means, the overall sample means. So, what we are considering here is a double summation over xij, the observations minus the sample, the overall sample mean, and the transpose of this, which can be shown to be a sum of the matrices like ni, summation of ni xi minus the group mean minus the overall mean, and what remains is the observation xij minus the group means, a term like this. Now, this can be easily established by adding and subtracting this group mean xi bar from the in this expression, and it can be easily separated. So, the term that we have in the left hand side is called the total sum of squares cross product corrected, and this is now equal to the treatment sum of squares cross product plus the residual sum of squares and cross product. Now, this treatment is essentially in the Manova parlance. Otherwise, what we had seen that this is nothing but our between sum of squares cross product, which means the variability between the different groups and populations, and residual is actually the within sum of squares cross products, that is within a particular population, and this is the corrected total sum of squares cross product. If we consider the uncorrected total sum of squares cross product, it means that we are not going to consider the deviation from the overall mean at it is. So, we can write it here that the total sum of squares cross product uncorrected is nothing but the sum of squares of the observations, which are xij transpose sum over both I and j. So, with this we can now form our Manova table and see the table is going to include. So, this is the Manova table for the one-way analysis, and we are going to have the first column is the sources of variation that we had mentioned in the beginning, that we are partitioning the variability into the different sources of variation. Then we have what is known as degrees of freedom, and next we have the sum of squares cross product, right. So, the first one is due to the factor. Here we are calling it as treatment. So, that is the treatment, no point in saying treatment 1, 2 because we have just one factor, and this is actually the between sum of squares cross product. And then we have the total. Total by default is going to mean the corrected total, and the rest of it is then automatically residual, which is the within sum of squares cross product. Degrees of freedom is for the treatment. We have how many populations? We have k groups, and -1. Now, this -1 is coming from we are losing 1 degrees of freedom because of the one constraint. Recall what is the constraint, that tau I hat I from 1 to k, this has got to be null, since our tau I hats are nothing but mu I hat minus mu hat. So, this constraint, this one constraint is resulting in the loss of 1 degrees of freedom, and the total degrees of freedom, next we look at it, is n minus 1. Total is total sample size from n, and here the loss of 1 degrees of freedom is essentially because of the taking of deviation. So, that we have, since we have a constraint like, since x bar is nothing but 1 by n sum of the observations I j, or the weighted means of the observations, you have, sorry, this is 1 by n x I bar. So, this factor coming into the into the factor of total, that is corrected sum of squares cross product, we are losing 1 degrees of freedom here, and then the rest can be calculated easily, and it is n minus k degrees of freedom for the residual. For the sum of squares cross product term, we know what we have is n I x I bar minus x bar x I bar minus x bar transpose. We denote this by the B matrix. The total is, well, we are not going to use it directly, but anyway we are going to write B plus W for the total matrix, and this is nothing but the corrected sum of squares cross product to total, the corrected one, and the residual is x I j minus x I bar x I j minus x I bar transpose I n j, and this is our W matrix. So, the total is nothing but the B plus W matrix. So, this is our ANOVA table, and we are going to test the hypothesis, that the null hypothesis that we test here, that the mean effects due to the treatments are all same, there is no treatment effect as such. So, these are all equal against the alternative, at least one inequality is there. And recall, now this is nothing but, if you see that this is, if you recall what our tau I hats are, what our in fact tau i's are, the parameters, these are mu I minus mu bar. So, this is basically equivalent to testing the k population means, which are mu 1 to mu k, and we have already done the groundwork for this. If you recall, we have tested, we have already seen how to test k population means when we are considering the normal populations. Okay. So, this is exactly what is happening here. By our distributional assumption, we have normal population, and we are testing the equality of k population means, but now in terms of the treatment factors, right. So, the test procedure remains essentially the same. If you recall our Wilks lambda criterion, it was lambda star, and it was given by, so recall that our Wilks lambda was nothing but determinant of W by determinant of B plus W, and the test procedure was that this rejects H naught if the LR test, that this is now, this is the basis, this is coming from our LR test. So, we can write the LR test rejects H naught if lambda star is small. So, this is essentially the exact test which we most of the time try to manage with the asymptotic test, if you recall, because we have a very nice result of the convergence of this criterion to the chi-square distribution. So, what we had was that we know the asymptotic test. So, let us just write, we can use the asymptotic test let us say tests, because we have one as it is the lambda test and another was the Bartlett's test. So, the tests are given by reject the null hypothesis if observed not the lambda star, but a slight variation, that is n log lambda star following, this is under the distributional assumption, and so we are giving the test criteria. So, this is greater than, if the observed one is greater than chi square p k minus 1, this was the degrees of freedom, and the Bartlett's test, or you can write the Bartlett's test has a slightly different constant term, that is n minus 1 minus p plus k by 2, and then we have log of lambda star, this greater than p k minus 1. Well, you may also write that at alpha level, so this is at 100 alpha % level of significance, where this is the upper alpha cutoff point of the chi-square distribution with the relevant degrees of freedom. Now, this is the second one is actually the Bartlett's test. It is better to use because it gives faster convergence. So, it is better approximation to the asymptotic distribution, that is the chi-square distribution. Now, we will list down the exact distribution in some of the cases. So, we have the exact distribution of the Wilks lambda available for some of the cases, available for specific values of p and k. Specific values of p, that is the data dimension, and k, that is the number of groups or population. So, these are, so first it is the data dimension or the number of variables, very plainly speaking, that we are considering, and then we have the number of populations or groups, whatever you call it, and then the test statistic and distribution. Now, these are available again for very specific values, very small values of p and k, that is low data dimensionality and fewer population groups. So, the first one is for p equals 1 and k is greater than equal to 2. If this is the situation, well, we are talking of the usual ANOVA then, because p equal to 1 means we do not have a multidimensional data. What we essentially have is unidimensional data, and then the test statistic is n minus k. Note that n is nothing but the total sample size, which is sum over n i's, and this is divided by k minus 1, the product with 1 minus lambda star by lambda star. So, obviously, since the rejection rule is for small lambda, here it will be for large lambda, and this follows f k minus 1 n minus k under h naught. The second one is for two dimensional data. So, that when we have p equal to 2, when we actually have the Manova, and then the same k for k greater than or equal to 2, that is 2 or more groups, then the test statistic is in the form of n minus k minus 1 by k minus 1, the product with 1 minus root of lambda star by root of lambda star, and this follows an F distribution with twice k minus 1 twice n minus k minus 1 under h naught is obviously there. The next one is giving a bound for this dimensionality. So, p is greater than or equal to 1 and giving a specific value. So, just the opposite situation of the first one, k is equal to 2 and p is greater than or equal to 1, we can use the test statistic n minus p minus 1 by P, the product with 1 minus lambda star by lambda star, this is going to follow an F distribution with P n minus P minus 1 under H naught, and then there is the last case where P is greater than equal to 1, which basically means we can use it for the unidimensional or the multidimensional case. There is an equality here and K is particularly equal to 3, that is for a very small number of groups or populations. So, earlier case was K equal to 2, here it is K equal to 3, and the test statistic looks like n minus P minus 2 by P, just a small change here, and here we have a 1 minus root of lambda star by root of lambda star. This is following an F distribution with twice P, twice of n minus P minus 1 under H naught. Now, the test procedure, the LR test, the exact likelihood ratio test we may add here in all the above cases. Is reject H naught if the observed F is greater than F at alpha with the relevant degrees of freedom. So, let us say that it is D1 and D2, whatever be the case, at 100 alpha % level, because as we said earlier, if the test is reject lambda when lambda star Wilks lambda is small, whenever we are defining the test statistic in this form, it has to be reject when it is large. Hence, the test procedure that we give in terms of the F statistic is the observed F is greater than the upper alpha % upper alpha cutoff point of the F distribution with the corresponding degrees of freedom. Now, if you recall the usual ANOVA where we have the unidimensional data. So, usual ANOVA, what happens? In usual ANOVA, one way, say we are still restricted to the one way situation. If you recall, the test statistic comes in the form of test statistic is the F, which is the sum of squares treatments, right, divided by its degrees of freedom and divided by sum of squares residuals divided by its own degrees of freedom. So, this follows the F distribution with the respective degrees of freedom. For treatments it is k minus 1, for residuals it is n minus k under H naught. Well, H naught remains the same, that is you have equality of k treatment effects. These are no longer vector valued, but these are scalars now, because we are talking of the usual ANOVA, and the F statistic is always in this form, and the test procedure is we reject H naught if observed F is greater than F alpha at k minus 1 degrees of freedom. So, this is at 100 alpha % level. Right. Let us look at a data example, okay, an example or an example with data. Let us start with one way ANOVA. In the data example, note that we are going to start with a one way ANOVA, that is basically we are going to start with random observations which will be one dimensional, and at the second stage to explain the Manova we will add one more data dimension to it. So, from p equal to 1 we will move higher to p equal to 2 and then totally explain how we get the Manova analysis statistics explicitly. Okay. So, the first case is for the univariate data, and we consider say the following independent populations, following independent observations from populations. So, let us say the independent samples, and we have from group or population 1, we have say 3 observations 9, 6 and 9, a very simple example. Then from the second group or population 2, we have 2 observations say 0 and 2. These are pertaining to some variable, some factor. We are just laying stress on the data itself. Later on we can take up a more practical example which will have better interpretation to the data. And the third population or third group have it has 3 observations 3, 1 and 2. So therefore, I can say few things from here, that k number of groups is 3, we have 1, 2 and 3. I can say what are my ni's. So n1 is 3, n2 is 2 and n3 is again 3. 3 to 3 observations. So that total observations is 3 plus 2 plus 3, that is 8. I can also calculate the group means. So the group sample means are, once we have the observations given in totality, there is no problem at all. So group sample means, if I try to calculate, the first one is x1 bar and it is nothing but the mean of the sample mean of the first 3 observations or the 3 observations from the first group, and that is 8. Similarly, I have x2 bar which is 1, x3 bar is nothing but 2, giving me the overall sample mean x bar is 4. I have univariate data, so the group sample means and the overall means, these are also scalar valued variables. You can see very easily that these are unidimensional. The values are 8, 1, 2 and 4. Now we go to the sum of squares splitting. So we do not have the cross product term here because we are dealing with unidimensional data. So sum of squares splitting is sum of squares total or total sum of squares uncorrected. So before that, if you realize that what my observation are, so how can I look at a single observation xij, that is a jth observation from the ith group? Well, I look at it as made up of x bar and then I have xi bar minus x bar and then this is xij minus xi bar, and then it becomes easier for me to consider the splitting. So I have sum of squares, the total sum of squares uncorrected is nothing but sum of squares of xij square, a double summation over I and j, and this is nothing but 9 square plus 6 square. I go on taking the square of the observations 1 square plus 2 square, which gives me 216. I am not exactly interested in this, but instead I am interested in total sum of squares corrected. Corrected means that from each of the observations I have to consider its deviation from the overall sample mean and then consider their sum of squares. So this is xij minus x bar whole square, and this is, if I take out 4 from the first one, I have 5 square plus 2 square. In this way I go up to 1 minus 4, that is giving me minus 3 square, and 2 minus 4, that is minus 2 square, and this is coming to 88. Okay. And if I write with df, well, df is nothing but n minus 1, which is 8 minus 1 equal to 7. Now I consider the treatment or the between sum of squares. Treatment sum of squares, if you recall, is nothing but, it is just summation of tau I hat square, which is nothing but summation of xi minus x bar square. So I have xi minus x bar square, but obviously I cannot forget this ni. So this is giving me, I have thrice. I have the, this is same for the first ith population. So, for the first population, note that xi bar is 8 whereas x bar is 4. So, I am going to have 3 times 4 square, and then I am going to have 2 times xi for the second, xi bar for the second population is 1. So, 1 minus 4, that is 2 times minus 3 square, and then again 3 times 2 minus 4, that is minus 2 square, and this is giving me 78 with degrees of freedom equal to k minus 1, that is 3 minus 1 or 2. And similarly, well, there is, strictly speaking, there is no need for me to calculate the residual sum of squares. Now, I can simply consider the difference between the total corrected total sum of squares and treatment sum of squares to get it, but if for verification's sake you can also do that, and what you have to consider is actually sum of these sum of squares of these deviations xij minus xi bar. So, what you can do is from each observation take out it from the first observations from the first group, consider the deviation, that is 8 in all the 3 cases. So, first you have 1 square and then you have minus 2 square, and for the last group you have these observations. From each of these observations you are going to consider the deviation from x3 bar, that is 2, and you are going to have the last 2 observations I am writing as minus 1 square and 0 square. So, that is giving you 10. It has to give you, because 88 minus 78 is 10, with degrees of freedom is equal to n minus k. So, let us write that in numbers. N is 8 and k is equal to 3, which is giving me 5. So, we have split up the sum of squares due to the treatments, due to the residuals and due to total corrected, and we have also obtained the corresponding degrees of freedom. Now, we know what is the hypothesis that we are testing. The null hypothesis that we are testing is nothing but tau 1 equal to tau 2 equal to tau 3 against the alternative that at least one inequality is there. Right. And this is the usual ANOVA. So, we can just simply consider the F statistic, the statistic that is used for this purpose, and which is sum of squares treatment, which is 78 minus its degrees of divided by its degrees of freedom, which is 2, the whole divided by the sum of squares residual, which is 10, and divided by its own degrees of freedom, which is 5. So, this is the test statistic, and this follows the F k minus 1, that is 2, n minus 1, that is 5 under H naught. So, our test procedure is reject H naught if observed. Now, let us see what is observed F here. So, observed F here is 19.5, it comes out to be 19.5, and the tabulated F at 0.01 with 2 and 5 degrees of freedom is having the value 3.78. Therefore, under the light of the given sample, reject H naught, the null hypothesis, at 1% level of significance. So, we are rejecting the null hypothesis that there is no treatment effect, the means coming from the treatments are all equal. We are rejecting the null hypothesis. Now, what we are going to do is we are going to extend the dimensionality of the data, going to make it 2-dimensional, just add one more variable. This is, plainly speaking, this is just adding one more variable on which data are compiled or on which data are collected to make it a 2-dimensional case, so that we can apply the Manova technique here. So, we had, recall we had our data as, now this is the extension, suppose an additional variable is observed. Okay. So, now the data dimensionality goes up to 2, p equal to 2. So, let us look at the data first. Now, if you recall, we had 3 populations, everything else will remain same. The first population or group, it had the observations, if you recall, as 9, 6 and 9, scalar valued observations. Now, we are saying that we are making it vector valued. So, we have information on one more variable, and hence the first observation from the first population is now a vector 9, 3. Similarly, I am adding the information on the same data to all the observations of the first populations. So, I have this completes my observations from population 1. So, next is population 2. If you recall, the observations were 0 and 2 in the unidimensional case. I am including information on one more variable, hence my observations, the complete observations are now becoming 2 dimensional, 0, 4 and 2, 0 say. And the third one is, if you recall, the observations were originally 3, 1 and 2. So, that I am adding one more line to them, making the complete observations 3, 8, 1, 9 and 2, 7. Now, let us see what are the information that I have from here. So, as before, my n1 remains 3, then n2 remains 2, right. This makes a complete observation 0, 4 and 2, 0 makes another complete observation. So, that n2 is 2 and n3 is 3 again, and so that the total sample size is 8. Number of groups or populations, well, I have stuck to 3 populations or 3 groups. So, I have k equals 3, and now the group means, group sample means, okay, which are essentially x1 bar, x2 bar and x3 bar, but unlike in the earlier case, these are now going to be vector, because I have x1 bar is nothing but the mean of these 3 observations. So, this is giving me 8. 8 was already there, we had already obtained 8 from our earlier calculation. Now, we are calculating only from for the second line, second element of these observations, and this average is giving me 4. Similarly, for x2 bar, the first element I already know that was 1, and now 4 and 0 I consider the mean of these, and I am getting 2, and x3 bar is giving me 2, which was already there, and the next entry is 8. So, that x bar, the overall sample mean is 4. Again, it is there, I can directly use it from my ANOVA calculations, because I have not changed the first line of the data anywhere. So, all these values remain the same, and this is the situation that I have. So, as before, we are going to now repeat the sum of squares operation for the second variable that we have now considered, the newly considered variable. So, we have sum of squares, total, uncorrected, exactly the same operation repeated for the second line of data, and this is going to give me 3 square plus 2 square up to 9 square plus 7 square, and this is adding up to 272. By the way, the degrees of freedom for this is full n, it is with degrees of freedom equal to 8, but we are really not using this. Again, total sum of squares corrected is, we have to take the deviation of the sample, overall sample mean from the observation, the sample mean now which is coming in the as the second entry of the vector of the sample mean vector, and this is going to be minus 2 square minus 3 square, this is going up to 4 square plus 2 square, giving me 72 with degrees of freedom equal to 8 minus 1, that is 7. And then we have the sum of squares treatment, sum of squares or the between sum of squares. This is now simply 3 times, as we have done the earlier case, 3 times minus 1 square plus 2 times minus 3 square plus 3 times 3 square, and this gives me 48 with df as k minus 1, which is 3 minus 1 or equal to 2, and then the residual sum of squares or the within sum of squares, and this again is as before, we have minus 1 square plus minus 2 square. This is essentially again for cross checking, because once we have got total square correct sum of squares corrected and treatment sum of squares, we did not calculate this, and this is minus 1 square giving me 24. So, 24 plus 48 adds up to 72, and degrees of freedom is n minus k, that is 8 minus 3, which is 5. Okay. Now, in order to complete the Manova table, now this is not ANOVA that we are using, testing it for unidimensional data. We have now multidimensional, 2-dimensional data. So, to complete the Manova table, it is not enough that we have got the sum of squares values, but we also need the sum of cross product values to complete the data matrix. Okay. So, let us see how do we consider the sum of cross product calculation. So, what we are going to consider is now the sum of cross product. So, just like the sum of squares total etc., we have total sum of cross product, sum of cross product. So, just one S is enough, uncorrected. What we do is essentially we consider the product between the first and the second, and then we get, what we get is 9 times 3 plus 6 times 2, and this goes up to 1 cross 9 plus the last one is 2 cross 7, and this gives me 149. Total sum of cross product corrected. Now, we have to consider the deviation, whatever the values that we have. After considering the deviation, consider them and then consider their products. So, it is like 5 times minus 2 plus 2 times minus 3. In this way, minus 3 times 4 plus minus 2 times 2, giving me minus 11. So, sum of squares, as long as they were, we did not have any minus or negative terms, but so these being cross product terms, we can have negatives as well. And then we have the treatment or between sum of cross products, treatment sum of cross products. This will be 3, which is the number of observations, the common number of observations in the first group. So, that is 3 times 4 into minus 1, for the second population 2, and then it is the common value minus 3 with minus 3. Then for the last population it is 3 with minus 2 and minus 3. So, this is giving me minus 12, and then the last one is the residual sum of cross product or the within sum of cross product, and that is 1 times minus 1 plus minus 2 times minus 2. So, this is going up to minus 1 with 1 and 0 with minus 1, giving me 1. So that these two add up to minus 11. And now I can form the Manova table. Let us go to the fresh page to form my Manova table. So this is for one way, right. I have the sources of variation, the first column, then we have the sum of, well, we have the degrees of freedom, and then we have the sum of squares and cross product matrices now instead of a scalar. So, the first one is due to treatment, the treatment effect, 3 of them minus 1. So, degrees of freedom is 3 minus 1 equals 2. Then due to the residual is the error present in the model, and that has degrees of freedom n minus k, that is equal to 5, and the total variability in the data, that is split up into these two factors. So, total is n minus 1, that is 7. And let us look what are these matrices. The first one is, well, I have sum of squares treatment for the first set of data, which was, if you recall, which was 78, and sum of squares treatment for the second observed second variable, which was 48. The off diagonals will be the sum of cross products, that is minus 12, and this is a symmetric matrix, this is minus 12 again. Similarly, the sum of squares cross product matrix for residual, if you consider the sum of squares residual from the first variable, that was 88, for the second variable it was 72, and the, I am sorry, I am writing the total here, the residuals will be, this is the complete matrix, this is our residuals matrix. So, this is 10 sum of squares residual from the first variable, from the second variable 24, and the off diagonals, that is sum of cross product was 1, and for total it is now 88. You can simply add up these, 78 plus 10 giving me 88, 48 plus 24 giving me 72, and these are giving me minus 11, and you can check it from your calculation. So, we call this matrix as our, if you recall, it is the between sum of squares cross product matrix. So, this is between, and this is the within sum of squares cross product matrix. So, this is our between plus within matrix. And then recall what your the likelihood ratio criterion, the lambda star Wilks lambda is nothing but determinant of W by determinant of B plus W. So, this is essentially determinant of the matrix 10, 1, 1 and 24 divided by the determinant of the matrix 88, minus 11, minus 11, 72. And then we get the value of this as 0.385. Now, what is the situation we have here? We have p equal to 2 because we have 2 dimensional data and k equal to 3. So, we can use the exact test, one of the exact tests that we had stated, right. So, there exists an exact LR test for this case, and just check that the test statistic in that case is nothing but what we are going to use is the test statistic for the case p equals 2 and k is greater than equal to 2, that case. So, the test statistic for that was n minus k minus 1 by k minus 1, that is for p equal to 2 and k greater than equal to 2, and this is considered with 1 minus root of lambda star by root of lambda star, and this follows an F distribution with degrees of freedom twice k minus 1 twice n minus k minus 1 under the null hypothesis. Okay. So, here it is equality of treatment. Now these are now vectors tau 1 to tau k. So here observed value of the test statistic f is nothing but 8 minus 3 minus 1 by 3 minus 1, and then we have calculated this Wilks lambda. So this is nothing but 1 minus root of 0.385 by root of 0.385. This is giving me the value 8.19. This I am going to compare with the tabulated f of degrees of freedom 4, that is twice k minus 1, that is 2. So, this is 4 and n minus k minus 1 is n minus k is nothing but 5, and 5 minus 1, that is 8. At level 1% level, this value is equal to 7.01. So, this is greater than tabulated f at this. So, we reject H naught, that the 3 treatment effects are equal at 1% level of significance. Right. So, after the ANOVA test, we augmented the data dimensionality by 1 and we did a Manova analysis, a one-way Manova analysis, and we arrived up to our test criterion with the help of the Wilks lambda. Well, we could have used the asymptotic test in this case, because we have said that in most of the situations where we use the likelihood ratio test, we go for the asymptotic convergence and use the chi-square distribution. But since in this case particularly we had the simple situation of p equal to 2 and k equal to 3, we chose one of those 4 exact tests given to us, provided to us, and we have gone by that test and we have reached the rejection. We have reached our decision that we are rejecting the null hypothesis of the equality of treatment effects at 1% level of significance. Okay. Now, this is essentially a typical data example. I have not given you proper interpretation of the data. We have to think of some variable 1 which has values 9, 3 etc. for the first population, and then when it is augmented by one more variable. So, we have to think of 2 variables which have got values like this. So, let us talk about a very practical example, our real data, and see how this Manova analysis actually helps us in getting some useful analysis from data. Okay. So, this is a practical example. Of Manova. The setup is something like this, that in a certain US state you have hospitals or clinics. These can be hospitals can be classified on the basis of ownership. So, these classifications are private, non-profit organizations, and government. So, 3 different classifications of ownership of hospitals, and also they may be classified according to the certification that they have received, and certification, that is, some of them are certified to be highly sophisticated, or just sophisticated, or with moderate care facilities. Right. So, there are essentially two factors on which data have been collected about the different hospitals in a particular US state. First factor is the ownership factor. There are three groups under this factor. One is the private ownership, the second non-profit organizations, and the third is government ownership. And then we have a second factor also, that is the certification that these hospitals have received, and they have been certified as highly sophisticated, and moderate, giving moderate care facilities. Now, what we do is so an analyst, the study is to essentially a study is conducted to find to investigate the effect of ownership or certification or both, in fact. So, this is, if we say, now the one thing that we can stress upon is that these two factors that we have classified, that is ownership and certification. Now, there can be several other factors on which data can be compiled and collected, can be separated, but at the moment we are going to talk about these two factors, and then we conduct a study where we first investigate the effect of ownership or certification. This we can handle with our one-way Manova. But if we go for the effect, if we go for the effect of both, now this cannot be handled with the one-way Manova. We have to consider the two-way Manova for this. Okay. So, initially we will say that we are going to investigate the effect of either this factor or that factor. It is either ownership or certification. But again I say, if I want to look at the effect of both or the combined effect, we have to go to two-way Manova, which we have not yet handled. Okay. So, a study is conducted to investigate the effect of ownership or certification and on costs, that is costs to the hospitals. Now, I am saying that I am considering not an ANOVA, but a Manova. So, obviously costs will have to be more than one. So, we are actually be considering four types of costs to the hospital. So, that the data dimensionality in this case is actually 4, and hence we are talking about a practical example of how to handle a 4-dimensional one-way Manova.